In the previous segment, we saw how treating the electron as a standing matter wave around the positive nucleus correctly predicted the discrete emission spectrum and absorption spectrum from hydrogen. We really only need one other big idea to understand how this can apply to a multi-electron atom. So let's look at a hydrogen atom and how that compares to a multi-electron atom for the first few energy levels. In hydrogen, we have our energy levels, 1, 2, 3, 4, and again, given the rules that we learned in the last segment for our quantum numbers, we see that we've got the 1s here, and then in the next energy level, the n equals 2 energy level, we could have the s or the p orbitals. In the energy level 3, we have s, p, and d. Now, in the hydrogen atom, all of the different orbitals have the same energy within a given energy level. In other words, the 4d orbital has the same energy as the 4s orbital. However, in a multi-electron atom, it's not quite that simple. Because there's all these other electrons involved, we get this splitting of the orbital energy levels. And so we find that the 2s and the 2p are not at the same energy. And so this is why we have these rules like we learned in chemistry. If you've already had chemistry, this is a review. If you haven't had chemistry yet, you can look forward to this. Okay, so how do we fill our energy levels as we add electrons to create multi-electron atoms? Well, if we have hydrogen, of course, it just goes in the 1s. Right? Helium, we have 1 in the 1s, 1 in the 2s. Lithium, we have 1 in the 1s, 2s, 2p. For beryllium, we pick up the 3s. Boron is next. We go to the 3p, but guess what? We don't fill up after the 3p. For carbon, we don't go to the 3d, we go to the 4s. Why? Because the 4s is at a slightly lower energy than the 3d. And we see that here. The 4s is actually lower energy than the 3d. So now we know why this pattern works. It's because in multi-electron atoms, the electrons are interacting with the other electrons, and it causes this splitting of the energy levels. And the atom will fill up its energy levels from the lowest energy to the highest energy. So why do they fill up here, right? Why don't we just end up with all of the electrons in the 1s state? Well, that's really a good question. I thought of it myself. Well, the way we kind of wrap our brains around that one is this idea of the Pauli exclusion principle. In the previous segment, we came up with the 4 quantum numbers that describe the state of an electron. The Pauli exclusion principle says that no 2 electrons can have the exact same set of 4 quantum numbers. So, if we were going to look at, say, helium, of course helium is number 2, and helium on the periodic table. And so helium has 2 electrons. Where do those electrons go? Well, the first electron goes in the 1s state, and the second electron can go there too, because we have spin up and spin down. So, for example, these 2 electrons right here, they have n equals 1, L equals 0, M sub s equals 0, and then, so those are all the same for both of those, but then we have spin up and spin down. So these 2 electrons have 3 out of the 4 quantum numbers the same, but that 4th is different. And so this is okay with the Pauli exclusion principle. What we could not have is a positive spin and another positive spin. You'd never have 2 electrons like this in that orbital. You would have them like this. Okay? So we could take helium and we could cause it to be in an excited state, in which case this electron would jump maybe up to the 2s, for example. In the lithium atom, here might be a ground state. Well, why doesn't this electron just live down here? Because then it would have to have exactly matching quantum numbers. Those 4 quantum numbers would match one of these other electrons. So it has to go in the 2s state. It could get excited into the 2p state. That works just fine. But the ground state then involves an electron in this higher energy level. In other words, for multi-electron atoms, The ground state might involve electrons up into these higher levels because you cannot just cram them all into the lowest energy level. So the ground state might include electrons in the 3s if you've got enough electrons to fill it up. Whereas for hydrogen, the ground state is always the 1s. So just like we saw how this idea helps us structure this diagonal pattern that you may have learned in chemistry, it also gives us a clue as to the structure of the periodic table, which I think is super cool. This first row is filling up the 1s shell. And what do I mean by that? I mean, imagine in our mind that we're adding electrons in order to create atoms with higher and higher atomic number. So in order to create hydrogen, we just put one electron in the 1s. In order to create the ground state of helium, we put one electron with a positive spin in the 1s and an electron with a negative spin in the 1s. Now my s shell, my 1s shell, is full. So now I'm going to fill up my 2s shell. Of course, I can have spin up and spin down in my 2s shell. In the 2p shells, we have n equals 2. And the p orbital corresponds to L equals 1. Okay, so we know that all of those electrons have n equals 2 and L equals 1. Now, at this point, though, we can have either an m sub s of what? -1, 0, or 1, because m sub s can go from negative L to positive L. We could have spin up and spin down, or +1/2 m sub s, or -1/2 m sub s. So we've got spin up, spin down, spin up, spin down, spin up, spin down. There are 6 combinations of quantum numbers that can be allowed in the n equals 2, L equals 1 orbital, also known as the 2p orbital. Again, the quantum mechanical model of the atom is correctly predicting the structure of this periodic table, which was discovered in like 1860 something. That's pretty cool. Moving along, we see the 3s shell fill here, and next comes the 3p shell. Next comes the 4s shell. Again, the 4s has a slightly lower energy than the 3d. And now that we're into the d shell, of course, we can get m sub s values all the way from -2 to +2, and so we can fit a whole bunch of electrons into a d shell. The true structure of this periodic table actually stretches out, right? If we had a big, wide piece of paper, we would probably stick this right into here. And those show the F shells filling. So that's pretty cool. Again, more evidence in support of this quantum mechanical model of the atom that we've been developing. So we can structure this way. This looks, this slide and this slide really go together. We can see how the different energy levels fill up as I add atoms in order to create larger and larger atomic numbers. Okay, so that was the one big idea, was the Pauli exclusion principle. So the standing matter waves around the nucleus and the Pauli exclusion principle, now that allows us to build up the structure of the multi-electron atoms, to understand the structure of the multi-electron atom.